Okay, remember what a histogram is. It shows frequency distribution. What does that mean? I'm going to show you how to do this, but in a minute. See, a frequency distribution means, for example, in this chart, 28% of the data points are under here, and 38% are under here. And if you add up all the frequency distributions, it will always be 100%. Okay. Now, like a normal curve, if you did calculus and you calculated it's called the definite integral from one side of the chart to the next, it would be 100%. So it's like probabilities. Contrast that with the histogram. I mean, the bar chart. See this? See this? Well, I don't have the numbers on here, but here, this is just the bar chart. Okay, how is that different than histogram? Well, it is just a count here. I didn't annotate it. Maybe we can do that. But like here, you know, for value 1, here's the point, 1, 4, 2, 3. So it's not probability density. It's just absolute count. All right, now let's go back and see how we did this. Okay, so it turns out the histogram function is very complicated. The complicated part is this thing called bins. See, but okay, so when I run this let's do it like this. When I run a constructor, a histogram, the complicated thing is calculating the edges. Okay, so let's just do this here. Let's just so look, see. So we can make a histogram many ways. We can just say, okay, let's run this a second. See this data that we have here. We have an array, right? We have 1, 2, 3, 4 ones, 3 twos, however many 6s and however many 4s. Okay, what the histogram does is it calculates that. It counts them by value. See, it's got space between it, kind of easy to read. But then there's some things that bother you about it, you know? For example, you know, it starts at 1 and it ends at, 1.3. Where did it get the width from? Well, it turns out that term is a complicated thing in histograms. If you go down here, see this one? I made the bins, it's called the bins. I gave them a specific value. Now I'm gonna move half of it down below. I don't want to plot the chart yet. Okay, so first, the histogram is really kind of a numerical thing. If I run this, okay. Oh, it drew the picture already. Okay, it did the plot. And if I say counts in bins, what's it gonna do? See? Okay, so it says well, it says the first point is 1, 4. So it's saying that the number 1 is in here 4 times. 1, 2, 3, 4 times. Okay, but see how the edge it calculated? It calculated edge to be 1.3. This is the difficult topic to do with quartiles, which are multiples of 25% in statistics. But we'll forget about that for a minute. Now, the next one we can see is 2. See, this says 0, 0, see? So here there's nothing here, right? Nothing, nothing. Till we get to 2, then it says 3. So it's saying we have 3 2s. Go up here and look. 1, 2, 3, 2, see? And so forth. Now, I could also just have done this. I could have said, I could say a histogram of X. Let's see what it does here. Let's see what kind of chart it will make. It did it so fast. It made basically the same thing, didn't it? Now, if I want, if I wanted to draw the boundaries, a specific location, I have to say what bins. So I'm going to say bins. I'm going to say start at 1 because the lowest value is 1. Then I'm going to say end at 5. Why not 4? Because it's not drawing just a skinny line with width of 0. It's drawing a wider line. So let's run this and see what it looks like. See, now look, that's what that looks like. It's a little easier to read, but not really easier to read. We could also do this but see, now that's not very easy to read either. I mean, I think you could put edges on it. But let me go down below and see how I made the next one. Okay, this one I did it like this. Okay, so right here I said histogram. I want the edges to be, well, it's sort of the same thing. I said, look at this Numpy array, get the minimum value. What's the minimum value in this array? It's 1. What's the maximum value? It's 4. It's saying shift it to the left by half, and then make the maximum be to the right a little bit. So let's see what it looks like. Let's run it. So remember what I said. The bar is not just a skinny line. It's going to have some width to it. Here the width is set to be 1. Now we started at 0.5, and then we ended at 4.5, right? We told it that here. So above, it calculated bin edges by itself. And when it did that, it looked kind of funny, right? It looked like this, you know? We could say, we could ask it, what are the bins here? Well, there are the bins right there, right? They're not integers. They're real numbers. See? I have to run this again. Bins. So that's what it came out with. 1, 1.3, 1.6. To put a little space between them, maybe to make it easier to read. But then here I'm telling it, I'm saying, I know what bins I want to use. I want to use, okay, this function here, okay. Can you understand what that does? What does NP A range do? This has 3 arguments. Why does it have 3 arguments? Let's put a 2 in here, see what it looks like. I spelled it wrong. Oh, that's true. That makes sense. That's not an array. We want it to make an array. 0, 2, 4. So if we make it go 15 by 2, it should put more of them in here. It's just a way to make an array, right? Now here we're saying to make it, to be the minimum number. And then we go to the left by half, why? Because it's wider than 0. So here it's going to start at 0.5, right? Each bar looks like it's going to be one interval or the number 1 wide. Then the end we say the maximum number, which is 4, and then it ends at 5.5, which is not on the chart. Then it says multiples of 1. Okay. Now let's see what else is on here. Okay, so we want to add to the chart some information here. We want to add this information. 19%. So how do you calculate this, first of all? Okay, what? So let's think about this. Let's see. What is an X? Okay, so we can do this. We can say, is it unique? Right, that's the unique numbers. Now, wait a minute. Let me look it up because I did it over here. I see. Okay. Return counts true. So this is gonna, if I do this, whoops. This is actually like a histogram. We'll call it hist. Well, actually, it's going to be the counts and then the values. So it's going to count how many 1s do we have? How many 2s do we have? Okay, then let's print them. So what is it saying? This is not a frequency distribution. What is a frequency distribution? A frequency distribution is a plot of, okay, for every number n, it is n divided by the sum of all the n's, right? How do we turn this into a frequency distribution? Well, for example, we know we have 4 1s. So what is the frequency of 1s? Should be 4 divided by what? How many values do we have? How many values do we have? This? It's the length of x, right? 21. So 4 divided by 21 should be that first number up here. See? Let's go back and look, see what it put. 19%. You see how that works?
Yeah, it's just the percentage amount of total.
That's right. That's what a frequency distribution is. That's what a normal curve is. It's a frequency distribution. Now, the only other thing that we did here is what you already know how to do. For example, well, here we did it with code, right? We said total observations That's how many values are in X. Calculate the percentage of each bin. So it's taking the counts here. Let's see what it did. We'll copy it down below. I think it should say, you know, for I and what was it? What were they were count? No, it was the values in values. Print I divided by the length of X. That's what it looks like it's putting at the top. Whoops. I gotta put parentheses here. Right? That's what it's printing at the top, see? $19, $14, $28, $38. How much time do I have left? Okay, I got plenty of time. The next thing I wanted to show you was, look what happens here if we do a normal curve. Suppose we do a normal, you know, where did I get these numbers from? I just typed them in. I typed in 1, 2, 3, type by hand, okay? What happens if we take random numbers from a normal distribution and we say 0 is the mean in 4 standard deviations. Now, what I've been saying is, now, look, you'll see that okay, and if you take calculus a lot, you say, you know, as n goes to infinity. This is called a limit, right? The definition of a limit. So look, I'm saying do a histogram with 50,000 values. Let me change this to be 500 and see what it looks like. It looks a little like a normal curve, right? So if you're looking at data and you think maybe it's normally distributed, you can just look at it. You can look at it and see whether it looks like a normal curve. Plus, we're going to learn some techniques for figuring that out as well. So see, the larger I make this number, the more it's going to look like a normal curve. Whoops, I forgot. That's Google, which is not running. I got to copy this over here. Put it over here where it is working. Okay. That's a pretty big number. Wonder how long it'll take to run on my computer. Maybe I made it too big. What I made it still running. I made it 500. I made it 500 million. Maybe that's too large. But anyway, while that's running, you can see here. Uh-oh, my computer's frozen up. Actually, Google did finish, didn't it? Okay, Google calculated a histogram of 1/2 billion numbers, see? And we can see when we plot them, that it looks like a normal curve. Why? It's got this shape, right? You see that?
Yeah.
Do you understand, Diana?
Yes.
Okay. Now, the last thing I want to show you, that okay, the histogram is the same as a bar chart, basically. See, when we tell it to do, you know, when we say use the matplotlib hist function, it returns counts and bins. Okay, this is the same thing. We can also use the Numpy unique function. Let's run this.